Hello, and welcome to episode 2.8 of Solarpunk Presents. Today, we're going to look at climate change from a totally different perspective, in a way that you've probably never thought about it before. But before we start, we need your support to keep this podcast going. So recommend us to a friend, write a review, or chip in a few dollars a month by supporting us at patreon.com/solarpunkpresents. Okay, there's one thing you need to know before we start, and that is that there are only 3 things that control Earth's climate temperature. One is, very obviously, how much energy is coming in from the sun. Second one is how reflective the Earth's surface is, meaning how much of that sunlight it's reflecting away instead of absorbing and warming up the climate. The third is how strong the greenhouse effect is, and so basically how much it slows down the escape of heat to space by trapping infrared radiation with molecules like carbon dioxide, methane, and water vapor. So, since the output of sunlight from the sun is a little bit out of our control, if you want a warm or cool climate, you either have to change the reflectivity of Earth, or you have to change the greenhouse effect. The second thing I'd like to say is that I've plotted up a lot of the data that I talk about during this episode, and if you want to see figures of things like temperature or carbon dioxide concentrations over the last 50 million years, I've put a link in the show's description. Now for the episode. Today, it's just me, Christina. I've put on my I used to be a professor of earth sciences hat to tell you about the Earth's last 50 million years of climate change. It's a complicated tale, but I'll try to keep it simple. To start with the 2-sentence summary, a long, slow, and not entirely explained decrease in atmospheric concentrations of carbon dioxide of more than 1,000 parts per million drove a 22 degrees C drop in average yearly global temperatures over 50 million years, plunging the Earth into glaciation. In Fahrenheit, that's a drop of over 40 degrees. That's kind of mind-blowing against the 1 degree of global warming we've managed to rack up by burning fossil fuels and destroying natural ecosystems. It also dwarfs the 2 to 5 degrees C of global warming that will come by the end of this century. But still, that 22 degrees C drop took 50 million years. So actually, we're off to a rather flying start in the climate change department. That's part of the reason that the people I know who are most alarmed about our present climate change are scientists who study the Earth's long-term climate history. They have a good idea of exactly how much climate change is possible within the climate system. And they, better than everyone else, know the complicated clockwork that is the climate system, full of side effects, feedback loops, amplifications, thresholds, teleconnections, and tipping points that mean eventually that last little small change triggers an explosion of consequences. This view of the climate system, once you have it, is at once incredible and humbling. It's awesome in the sense of the word that merges amazement with respect and a twinge of fear. But let's start off by talking about what the world was like before it started getting cold. So let's jump back to 66 million years ago, just before the asteroid slammed into the Yucatan Peninsula and did in the dinosaurs. The Earth at that point was hot and rainy. Even polar regions like Antarctica were warm, and they were covered in thick forests that we'd be more likely to describe as subtropical than polar. There were no continental ice caps, much less continental ice sheets, such as we have on Greenland and Antarctica today. And there was little in the way of glaciers, even high up toward the mountaintops. Seas were shallow and flooded up onto the continents. Flowering plants and their nutritious seeds and fruits, while no longer newbies on the evolutionary scene, were finely growing gung-ho. This was giving the earliest mammals, who were still small, mainly herbivorous or omnivorous, and did not yet include the marsupials and placentals that dominate today, food to specialize in eating. The flowering plants known as grasses were only just beginning to spread across the land. So that's a crazy thought. For most of Earth history, the world has not been covered in grass. But to get back to the end of the Mesozoic, Of course, Archosaurian reptiles, namely dinosaurs, plesiosaurs, and pterosaurs, dominated Earth's ecosystems. Avian dinosaurs, at least, inhabited every continent, including that lushly forested Antarctica, whose warmest summer temperatures could reach 30 degrees C, also known as 86 degrees Fahrenheit. A Tyrannosaurus rex stepping out of a time machine today could be forgiven for thinking, what the hell happened? Never mind the skyscrapers, the Earth today is cold, grassy, and overrun with mammals. During T-Rex's time, not just Antarctic summer temperatures, but average yearly global temperatures sometimes hit 30 degrees C, that 86 degrees Fahrenheit. That might sound comfortable to you, but actually that is absolutely incredibly hotter than now. And that's just the average. We don't even want to think about what the hottest summer temperatures in the hottest part of the planet might have been like at that time, if the average over the whole year for all the points on Earth was already 30 degrees C. But okay then, what are global average temperatures now? And the answer is 15 degrees C, otherwise known as 59 degrees Fahrenheit. That is an awful lot colder. And that's warm compared to the 8 degrees Celsius, or 46 degrees Fahrenheit, at the last glacial maximum 20,000 years ago, when we had much more ice in the northern hemisphere covering all of Canada and Scandinavia and so forth. The difference between the dinosaurs' time and now is even more extreme if you just look at the polar regions, where average annual temperatures are tens of degrees below freezing, instead of the 10 to 12 degrees C or 50 to 54 degrees Fahrenheit they used to be during the Mesozoic, that geological era that ended 66 million years ago. And the oceans, oh my. The temperature of the waters at the bottom of Earth's now deep and vigorously circulating oceans is more or less around the freezing point, rather than stewing at 20 degrees C, 68 degrees Fahrenheit, a Mesozoic warmth warmer than even most of the sunlit surface waters of the oceans today. Fun fact, today's climate is not just a whole lot colder than the Mesozoics, it's just plain old cold. We warm-blooded, well-insulated mammals find Earth's current climate reasonable, comfortable, and normal. And the ongoing global warming may soon render portions of the Earth only habitable to humans with air conditioning. But for 85% of Earth's history, Earth's climate has been warmer than it is now, sometimes to a mind-blowing number of degrees. So then, what the hell did happen? How did the Earth end up in this weirdly glaciated state, with large ice sheets present in both hemispheres, and 2 icy polar seas? Okay, we've reached the point in this episode where I have to tell you about foraminiferans. For the last few 100 million years at least, foraminiferans have lived in the ocean. Some live the life of the plankton near the surface, others hang out on the seabed. Quite a lot of these tiny, amoeba-like animals make what you would call a shell, although it's known to science as a test, out of the biomineral calcium carbonate. The relevance of this is that when the calcium carbonate precipitates out of seawater, it doesn't just nab calcium ions and carbonate ions and trap them in the matrix of the mineral, but also chemical signals that hold information about the environmental conditions. This then makes a recording in this shell or test of the foraminiferan of things like temperature or the pH of the water at the time the foraminiferan formed its calcium carbonate. Luckily for us, after foraminiferans die, their calcium carbonate tests can end up piling up on the seafloor. Over time, the calcium carbonate microfossils get buried by further sedimentation that's settling down on top of them. Eventually, scientists can come along and drill out a core of seafloor and obtain this nice stack of forams going back in time. They can pull out the little calcium carbonate microfossils, clean them up, and then analyze them in such nifty gizmos as multi-collector inductively coupled plasma mass spectrometers to unlock the records of past climate. It has taken decades of work, but analysis of literally hundreds of thousands to maybe even millions of forams from thousands of sediment cores taken from all over the ocean has revealed that Earth's climate began cooling from that dinosaurian warmth of the Mesozoic, not 66 million years ago, but 50 million years ago, We also know that the cooling between then and now did not happen in a straight line, but in stages and had some ups and downs, as if the climate system was stumbling between different phases of operation as factors like sea level, the position of the continents, the extent of glaciation, the concentration of carbon dioxide in the atmosphere changed, and feedback loops responded, and sometimes tipping points were crossed. Some of these phases were stable and long-lasting, some were short and sharp, others were somewhere in between. Even more excitingly, thanks to recent advances and our ability to measure the isotopic composition of one of the trace elements that occurs in the calcium carbonate, we now know the main reason climate got colder was that the atmosphere lost an incredible amount of its carbon dioxide over that time frame, over those 50 million years. So concentrations of carbon dioxide in the atmosphere declined from roughly 1,250 parts per million 50 million years ago, when it was super warm, down to 190 parts per million. That was 20,000 years ago at the last glacial maximum, when climate was even way colder than it is now. So that is a decrease of more than 1,000 parts per million carbon dioxide in the atmosphere, and that's absolutely whopping. Just as a point of comparison, over the last 150 years, we've added enough carbon dioxide to the atmosphere to increase concentrations by 139 parts per million, bringing the total to 419 parts per million by January 2023. This is a value for carbon dioxide in the atmosphere the Earth has not seen for several million years, dating back to when the Earth was still not cold enough to have any continental ice sheets in the northern hemisphere at all, which is worrying if you're a fan of the Greenland ice sheet. So, how warm was it 50 million years ago when the Earth had something like 1,250 parts per million carbon dioxide in the atmosphere? Answer is, like parts of the Mesozoic, it was 30 degrees C, or 86 degrees Fahrenheit, that number that we threw around before, this average yearly global temperature. That's more than 15 degrees C, or 25 degrees Fahrenheit, warmer than today. But 50 million years ago, there wasn't yet this huge gradient in temperature between the equator and poles that we think of as being totally normal. This means that the polar regions were way, 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 way warmer than they are today. Mid-latitude regions were closer to that average of 15 degrees C warmer, and equatorial regions were, a bit warmer than they are today, but, not by the full 15 degrees C. So, the Earth has never, ever again been that warm. And this is because carbon dioxide concentrations began to decrease 50 million years ago, and following from that, temperatures all over the planet began to fall. In the first step of the last 50 million years of climate change, carbon dioxide concentrations decreased to roughly 1,000 parts per million, and climate cooled from 30 degrees C to 23 degrees C, or 73 degrees Fahrenheit, between 50 million years ago and 45 million years ago. Excitingly, this cooling sowed the seeds for Antarctic glaciation, because it got cold enough for glaciers to sprout in the transantarctic mountains that separate the large main lobe of the Antarctic continent, which is East Antarctica, because it sits mostly in the eastern hemisphere, from the remaining third of the continent, known as West Antarctica, which sits on the Pacific side of the transantarctic mountains and includes the Antarctic Peninsula. We know about this growth from the ages of the scars these glaciers left behind in the mountains. During the second phase of cooling, carbon dioxide fell to 900 parts per million, and temperatures dropped to 20 degrees C, or 69 degrees Fahrenheit. This happened between 43 million years ago and 34 million years ago. Glaciers started showing up at increasingly lower elevations in the transantarctic mountains. Meanwhile, the glaciers at the highest elevations grew massive enough to fuse into large fields of ice. Toward the end of this cooling phase, some of Antarctica's glaciers even managed to reach the coast and were calving icebergs off into the ocean. We know this from the stones and other continental debris that the icebergs dropped on the seabed far out to sea as they melted. Then, bam! 34 million years ago, glaciation tore across East Antarctica. Why? Because global temperatures had decreased to the threshold where an Antarctic ice sheet was possible. In just a few thousand years, Antarctica's glaciers and isolated ice masses grew into an ice sheet that sprawled across East Antarctica. All this ice sent global temperatures plunging, thanks to all of the sunlight it reflected back to space, preventing it from warming climate. It took 1 million years and a cooling of 2 degrees C for climate to stabilize again. And stabilize it did. Earth's climate remained at around 18 degrees C or 64 degrees Fahrenheit for the next 20 million years. Temperature-wise, this was the halfway point in the cooling from the 30 degrees C of 50 million years ago to the 8 degrees C or 46 degrees Fahrenheit of 20,000 years ago. But the atmosphere's loss of carbon dioxide marched onward. Climate cooled again starting 14 million years ago to 16 degrees C or 61 degrees Fahrenheit as carbon dioxide concentrations reached 500 parts per million. This triggered yet even more ice to add itself to the Antarctic ice sheet, expanding it in height and breadth. By 3.6 million years ago, with carbon dioxide concentrations now under 500 parts per million, and global temperatures below 15 degrees C or 59 degrees Fahrenheit, it was the northern hemisphere's turn to finally jump into the glaciation game. What had been mountain glaciers and ice masses on Greenland grew into an ice sheet that kept growing until it was like the one you can see out the airplane window as you jet over Greenland today. Eventually, carbon dioxide concentrations and climate temperatures decreased enough for the northern hemisphere ice sheet to massively expand. Okay, at the moment, anthropogenic global warming aside, climate is trapped in a phase where carbon dioxide concentrations oscillate between 280 and 190 parts per million over about 100,000 years. And climate goes from what we call interglacial to glacial conditions and then back again. At the deepest depths of the glaciations, not just Greenland, but most of Canada, Scandinavia, Great Britain and Ireland, and parts of the US, of non-Scandinavian Northern Europe, and of Russia are covered under domes of solid ice kilometers high, thousands of miles in length and breadth. During the deglaciations, this melts rapidly back to the remnants we have now on Greenland, or even less. Then the loss of carbon dioxide from the atmosphere, and the cooling and the growth of the ice sheets begins again. The reason for this insane oscillation between glacial and interglacial conditions is that the world isn't cold enough for permanent northern hemisphere glaciation. And part of the reason the oscillations are so extreme in terms of temperature and climate is the increasingly massive amount of sunlight that gets reflected back to space as the northern hemisphere ice sheets grow in area. So this interglacial that we're living in is actually just a less glaciated phase of a deeply glaciated state for Earth, even if northern hemisphere glaciation is just barely hanging in there. Or maybe it would be better to say, just getting started, because the million-dollar question, probably only temporarily interrupted by anthropogenic global warming, is the Earth done cooling? Or are the glacial-interglacial cycles the Earth is currently locked into merely the latest step in the last 50 million years of cooling? Or 60 million years? Or 70 million years? Or who knows how long it would keep going? So I'm going to give you a little spoiler alert, and I'm going to say, I think it would keep going for as long as we have the Himalayas and the Tibetan Plateau, the Deccan Traps flood basalts, and all of the basaltic islands in Southeast Asia that are in this sort of warm, wet, tropical location. In other words, I think the Earth is going to keep cooling for several tens of millions of years longer, at least once it gets over anthropogenic global warming. And now let's get to why I think that's true. For that, we have to answer the other million-dollar question. The other million-dollar question, probably worth rather more actually, given how much research money has been poured into investigating it over the last several decades, is why have atmospheric concentrations of carbon dioxide decreased by more than 1,000 parts per million over the last 50 million years, driving the Earth's climate out of the warmth that the dinosaurs enjoyed into the depths of a bipolar glaciation. And bipolar meaning you've got it not just in the southern hemisphere, but also in the northern hemisphere, situated at the poles. There is actually a super simple, if slightly unsatisfying, answer to this question of what's responsible for removing all of this carbon dioxide from the atmosphere. And that answer is the carbon cycle. It's the job of this particular biogeochemical cycle to transfer carbon between deep Earth reservoirs like the Earth's mantle and its surface reservoirs like the atmosphere. It's also the carbon cycle's job to shuffle carbon between the atmosphere and biosphere, the ocean, the animals and plants in the ocean sediments, the Earth crust and lithosphere. To put the carbon cycle briefly, driven by the tectonics that moves the continents around by creating new ocean floor at mid-ocean ridge spreading centers, volcanoes at mid-ocean ridges and arc volcanoes such as those of the Pacific Ring of Fire expel carbon dioxide from the mantle into the atmosphere. From the atmosphere, carbon dioxide can enter the oceans as dissolved carbon dioxide gas. It can enter the biosphere as organic matter, thanks to photosynthesis. Or it can get converted to carbonate and bicarbonate ions during the chemical weathering of silicate rocks like basalt and granite. Essentially what happens is carbon dioxide dissolves into rainwater or groundwater, gives it a bit of acidity, and then this helps dissolve these silicate rocks. And that process takes the dissolved carbon dioxide in the water and converts it to carbonate or bicarbonate ions. So ultimately, these carbonate and bicarbonate ions wash out to the ocean where they can be used to produce calcium carbonate biominerals that settle into the sediments. As tectonics chugs along, producing more ocean floor at mid-ocean ridge volcanoes, the sediments ride along with the ocean floor all the way away from that mid-ocean ridge to a subduction zone at the edge of the ocean, where they are returned to the mantle. As the slab of ocean crust, lithosphere, and sediments sinks deeper into the Earth's interior, it partially melts, fueling the arc volcanoes above the subduction zone, returning some of the carbon from the slab, so from the crust, the lithosphere, and the sediments, back to the atmosphere as carbon dioxide. And this has been going on for billions of years. These processes aren't perfectly balanced. So there's a lot of wiggle room, because you've got all these reservoirs, and they can expand and contract in size, right? You've got the biosphere, you've got the ocean water, and you've got the lithosphere, you've got the crust, you've got the mantle, and so on. Given all the different reservoirs involved in the carbon cycle and how dynamic their cycling is, it seems kind of amazing that we could ever have the right amount of carbon dioxide in the atmosphere to have the right strength of greenhouse effect to have a reasonable climate. But it turns out there's a mechanism for holding more or less the right amount of carbon dioxide in the atmosphere to prevent Earth's climate from wandering out of habitable bounds. Because the greenhouse warming from the carbon dioxide is really, really important for keeping Earth's climate from being too hot or too cold. Ordinarily, and this is one of the coolest things about Earth, and it's what makes Earth habitable, is that climate controls how fast silicate weathering turns carbon dioxide from the atmosphere into carbonate and bicarbonate ions. And this in turn controls the climate. So you've got this little thermostat here. Putting it roughly, when climate is warm, silicate weathering goes faster, converting more carbon dioxide into carbonate and bicarbonate ions. And this happens faster than the mantle returns carbon dioxide to the atmosphere via volcanoes. As a result, carbon dioxide concentrations in the atmosphere decrease over thousands to tens of thousands of years, and as a result, climate kind of slowly cools down. But of course, as climate cools down, silicate weathering rates decrease. And eventually, silicate weathering's consumption of carbon dioxide no longer exceeds this return of carbon dioxide to the atmosphere from the mantle. In fact, at some point, it's no longer even keeping up with it. Carbon dioxide concentrations begin to slowly build back up in the atmosphere. Climate cooling slows down. Then it stops. And then it turns back into warming, because you've got enough CO2 in there that you're insulating the atmosphere, you're preventing all this heat from going out, and things warm back up. And this causes silicate weathering rates to increase again. And so this is the nifty, if slowly reacting thermostat that has kept Earth's climate from wandering out of habitable bounds at any point over the last roughly 4.4 billion years. Except that during the last 50 million years, the silicate weathering thermostat has gone haywire. Even as carbon dioxide concentrations have kept decreasing and climate has kept cooling, consumption of carbon dioxide during silicate weathering has continued to outpace the resupply of carbon dioxide from the mantle. Not by very much every year, but when you've got 50 million years, it adds up. Thus have atmospheric concentrations of carbon dioxide decreased by those more than 1,000 parts per million over the last 50 million years, driving the Earth into an icehouse climate. So this is a pretty extreme thing to claim. How do we know it's true? So we know about the robustness of silicate weathering's conversion of carbon dioxide into carbonate and bicarbonate ions over the last 50 million years from those sediment cores we drill out of the seafloor. We can see that 50 million years ago, 70 million tons of carbon was being added to the ocean store of carbonate sediments every year. Right now, however, that number is 275 million tons of carbon per year. And such an increase in the reservoir of carbonate sediments would not be possible without the increasing delivery of carbonate and bicarbonate ions to the ocean via the weathering of silicate and also carbonate rocks on land. And here again, we've solved a mystery only to stumble onto a bigger one. Why did the silicate weathering thermostat go haywire over the last 50 million years? Why didn't silicate weathering slow down as climate cooled, thereby preventing carbon dioxide concentrations from decreasing? That would have stopped climate from cooling, and we would have never ended up with this glaciation that broke out in both hemispheres. Here's where our story starts to actually get complicated. Because, most likely, it took a constellation of events and factors coming together to derail the silicate weathering thermostat. If you're a planet and you've been around for 4.5 billion years or so, eventually you run into a bit of bad luck. Although it's far from settled science, here's a series of events that could possibly explain it. So the first thing that happened began well before 50 million years ago, and that is plate tectonics slowed down. This happens from time to time for a variety of geological reasons. The end result is, if you're making less new ocean floor every year, it takes older ocean floor longer to cross the ocean or to get pushed across the ocean to reach a subduction zone. That gives it many more millions of years to cool and thicken and accumulate sediments. That means it gets heavier and floats lower on the sea of mantle beneath it. As a result, the oceans get deeper. Okay, it took a while. Today, the average depth of the ocean is hundreds of meters deeper than it was, say, 120 million years ago. The deepening of the oceans meant that they could hold more water. That's why the seas are no longer shallow and flooded up onto the land like they were when the dinosaurs were around. And as the ocean waters receded back into the ocean, slowly over millions of years, they exposed all of this continental area to the possibility of silicate weathering. So, as the ocean slowly deepened, it became increasingly possible to do more silicate weathering at any particular given climate temperature. So that is, the first way you start to reset the thermostat to hold climate at a lower average temperature. And this is the first reason that silicate weathering rates began to more than compensate for the amount of carbon dioxide entering the atmosphere from the mantle, lowering atmospheric concentrations of carbon dioxide in the atmosphere and cooling climate. The second thing that happened was the Deccan Traps flood basalts, and they represent a massive volume of easily weatherable silicate rock that are now located in the warm, wet tropics and are cut through by some large, warm rivers. As such, they represent a perfect storm of possibility for weathering a lot of silicate rock quickly, even as the Earth's average global temperature goes down. The Deccan Trap story starts 66 million years ago. At that moment, the asteroid slammed into the Yucatan Peninsula, bringing about the end of the reign of reptiles. The asteroid hit with a hell of a smack, sending massive shockwaves across and through the Earth. One of the things that got all shook up was the plume of mantle that had been quietly rising through the Earth's interior on the other side of the planet. And mantle plumes happen all the time. That's why you have the volcanoes in Hawaii, for example. So one of the things that got all shook up was this plume of mantle that had been quietly rising through the Earth's interior on the other side of the planet. And so it suddenly, devastatingly penetrated the crust at the Yucatan's antipode, pouring out lava like you simply cannot imagine. Before the initial eruption was over, it had covered 1.5 million square kilometers, or 580,000 square miles, of the Indian continent, who was in the wrong place at the wrong time, under a layer of basalt 2,000 meters thick, or that's 6,600 feet thick, creating the geological formation known as the Deccan Traps. At the time, the eruption released a lot of gases and aerosols that, messed up climate and added nail to the dinosaur's coffin. But what's actually interesting here is that all that easily weatherable silicate rock that weathering got to work on and continental drift later weaponized, because basalt is really, really, really easy to dissolve. Easier than, say, granite, for example. So I say continental drift later weaponized because when the Deccan Traps flood basalt poured out, India wasn't where or what it is today. It wasn't yet docked against Asia, and there were not yet such things as the Himalayas or the Tibetan Plateau. Although that isn't to say that this portion of Asia wasn't already starting to build up topography as terrains successively docked against Asia as the Tethys Sea between India and Asia closed down. Having broke off of the half-supercontinent Gondwana, roughly 120 million years ago, which was centered around the South Pole, 66 million years ago, India was speeding northwards toward Asia, riding along with the closing of the Tethys Sea. When the mantle plume broke through India's crust in that massive explosion of volcanism, India had essentially reached the site where the Seychelles are today. So, starting somewhere between several and 10 million years later, which is to say about 50 million years ago, India began this collision with Asia, further thickening the terrain and beginning the uplift and erosion that brought us the magnificent peaks of the Himalayas and the Karakorams. The 100 or so peaks that soar over 7,200 meters, or 23,600 feet, into the sky, like nowhere else in the world. And enough rain began falling on what was becoming the Himalayas to funnel itself into large warm rivers that cut through these easily weatherable basalts, covering the 1.5 million square kilometers of India. And today we've got rivers like the Godavari, the Tapti, and the Narmada, and their tributaries that are still doing this work today. So, this boosted global silicate weathering rates, right? Easily weatherable basalts, nice warm waters percolating through them, and this accelerated the conversion of carbon dioxide into carbonate and bicarbonate ions, even as climate was cooling. This increased the concentrations of carbonate and bicarbonate ions in the ocean, giving this boost to the accumulation of sediments made of calcium carbonate that we see when we look at the sediment cores. Then over time, as the Himalayas kept growing and eroding, and the Asian monsoon grew stronger because of the configuration of the continent, and adding to this, the basaltic terrains of Southeast Asia came into existence, adding yet more basalt to Earth's pool of easily weatherable silicate rocks, weathering rates kept increasing even as Earth's temperature kept decreasing. In other words, thanks to the combination of the deepening seas and thus falling sea levels, the Deccan Traps flood basalts, the India-Asia collision, the formation of Indonesia through all of this volcanism, the amount of silicate weathering that can happen at lower global temperatures and result in carbon sequestration in deep sea sediments is now greater than possibly ever before in Earth history. And that's why we are in a glacial climate. This does not mean that the silicate weathering thermostat that keeps the planet at a habitable temperature has failed, only that it has been reset to stabilize the climate at a vastly colder temperature. This will remain true, at least until erosion and weathering manage to eat through the Deccan Traps, Indonesia, and the Himalayas. For me, there are a bunch of lessons wrapped up in all of this. For starters, we may like to lie by the pool, soaking up rays on warm days, but in truth, like our fellow mammals, we're creatures of the Earth in a shockingly glaciated state. And utterly unlike the dinosaurs, we thrive when the Earth is cold. Global warming is absolutely not where we want to be going. We're not built to survive it. But most of all, what this story of 50 million years of climate change means to me is that anthropogenic climate change, while monumental and catastrophic for all of Earth's currently living creatures, is just a blip in the history of Earth. At some point relatively soon, we'll either run out of fossil fuels to burn, or we'll just stop burning them. Over the next few 100,000 years, silicate weathering will convert all that carbon dioxide we spewed into the atmosphere into carbonate and bicarbonate ions, and a bit more calcium carbonate will end up in the sediments in the ocean. And someday, maybe 100 million or more years from now, all those carbonate sediments will end up being subducted back down into the mantle. In the meantime, climate will have settled back down at the temperature it's meant to be, as set by the amount of carbon dioxide in the atmosphere, which is designated by the maximum silicate weathering rate that is possible given the configuration of the continents, sea levels, and the availability of easily weatherable rock. Oh, and also by climate temperature. You and I, and possibly no other member of the human race, will live to see that day. But the Earth will, and so will its biosphere, which will recover from what we've done to it and go on to produce new species of all sorts of creatures that we can't even yet dream of. In the meantime, though, man-made global warming is going to be a bit of a challenge for us. It's going to be terrible, and we should do everything in our power to stop emitting greenhouse gases like carbon dioxide and also methane as soon as possible. Because the more of the total amount of carbon dioxide that we end up emitting, the worse this global warming is going to be for ourselves and everything else on the planet. And that's a wrap for episode 2.8. Thank you very much for making it to the end of this deep dive into a bit of science. I either hope you enjoyed it or you learned something or maybe a little bit of both. Don't forget to sign up for our Patreon. Thank you for listening to Solarpunk Presents,
a podcast hosted and produced by Ariel Kroon
and Christina De La Rocha.
The audio for this episode was recorded in part on the traditional territory of the neutral Haudenosaunee and Anishinaabe peoples,
and in Germany. The opening and closing music of this podcast is Water Cooler Gang by Monkey Warhol.
Available for use under the Creative Commons Attribution 4.0 International License.
Until the next episode,
keep dreaming
and keep up the good work.